Friends, today's subject of discussion is synthesis of ring system retrosynthetic strategy. We are going to discuss the retrosynthetic strategies adopted for six-membered ring synthesis. The first and foremost approach which is followed for the synthesis of six-membered ring system having a carbocyclic ring system is Diels-Alder cycloaddition. We know about this Diels-Alder addition reaction. I take a six-membered ring system of this sort. I'll break over here the carbon-carbon and carbon-carbon breakage. And this is 1, 2, 3, 4, 4 carbon donor, and this will be a 2 carbon donor. A 4 carbon donor will be a diene. And here alpha beta unsaturated ketone is a dienophile. A diene and a dienophile reacts together to give a Diels-Alder adduct. That is Diels-Alder cycloaddition reaction. This is an classical example of an electrocyclic addition reaction. Electrocyclic addition reaction is one such reaction in which there are no intermediates formed. The intermediates may be a carbanion, carbene, or a carbocation, or a free radical. For any reaction to occur, any of these intermediates should be formed. But these are the special reactions in which no such intermediates are formed. In these reactions, the electrons move cyclically to form the bond. The pi electrons over here moves towards this carbon and it has to maintain a state. Pi electrons again here moves to the next carbon and the pi electrons moves and combines with this carbon and cyclization occurs to give the cyclohexane ring system. This is the strategy followed for the synthesis of six-membered ring system. Another approach which we can follow is a complete reduction process. I have para-tertiary butyl cyclohexanone ring system. If I completely reduce this, the ketonic group gets reduced to alcohol, the cyclohexane ring reduced to phenyl. Para-tertiary butyl phenyl, I can break up over here. I'll get phenol as one of the starting materials. I take phenol and treat with tertiary butyl chloride in the presence of a Lewis acid catalyst like AlCl3. This OH is electron donating and ortho para directing, and para will be the position of attack preferably because ortho position, if it attacks, it forms steric hindrance and will get major portion as para tertiary butyl phenol. If I reduce this by using hydrogen and palladium, the double bond gets reduced. I'll get cyclohexanol, and after cyclohexanol, if I oxidize, I get cyclohexanone. This is the another strategy which we follow for carbocyclic six-membered ring system. One more strategy we follow. In this strategy, we reduce the ring system partially and achieve the formation of the six-membered ring. Here I have the molecule, a cyclohexane ring, and it is having an epoxide group over here, and here this is attached with a diol. I break over here. If I do epoxidation, I'll get cyclohexenone and I will break over here. Cyclohexenone. I partially reduce methoxy derivative, a double bond over here. I'll take anisole. I'll do partial reduction. I'll get corresponding 1,4 dihydro derivative. Further reduction. I do openier oxidation. I'll get corresponding cyclohexenone. I do epoxidation by treating with hydrogen peroxide and a strong base. The epoxidation occurs at the double bond. The carbonyl group I treat with ethane diol. This get blocked and gives this system. Another approach we follow is a ring opening reaction. If I want to synthesize cyclohexane directly I cannot synthesize. That's why I do fragment group interconversion. I take cyclohexanone. Again I do fragment group interconversion by adding COOET to ortho position. I break over here between the two functional groups. CC breakage. If I break over here, if this CO, I add OET 1, 2, 3, 4. CH2, COOET, CH2, C double bond O, OET 1, 2, 3. CH2 thrice and CH2, COOET. Diethyl heptane dioate. I can take and I can carry out the reaction. I take diethyl heptane dioate, treat with sodium ethoxide, Na plus, OET minus, abstract the proton from the carbon over here, creating a carbene ion. As this is electron rich and this is electron deficient, carbonyl carbon, this is electron deficient owing to the electronegativity of the oxygen. Is electron deficient, is electron rich. Unlike poles attract each other. This attacks on the carbonyl carbon. Pi electrons moves on oxygen O minus. O minus, OH. Oxygen is divalent, it is unstable. That's why to gain its stability, pi electrons, these excess electrons moves over to the adjacent carbon and ethoxy and easy leaving group gets kicked off. I'll get a carbonyl. COET which I am having here, I hydrolyze this in the presence of an acid. The COOET gets converted into COH and ethanol. I strongly heat it, decarboxylation occur, I'll get cyclohexanone. Treat with zinc amalgam and HCl, I'll get cyclohexane. These are the four strategies which are utilized for carbocyclic six-membered ring system synthesis. Next class, we can deal with other ring system containing different members like 4-membered and 5-membered. Till then, have a nice day. Thank you.